In this very short tutorial, I'm going to explain the meaning of Cohen D. Let me just start with that example. So there are two groups of numbers. The first group is 10, 20, 30, 40, 50. The mean is 30. And another group is all this number and the mean is 35. If we just calculate the mean differences, then is 35 minus 30 is 5. And the differences between the mean differences and Cohen D is that Cohen D on the top of the mean differences in the numerator, it also consider the standard deviation of the data. So here, since that the standard deviations are the same for both groups, so the denominator is just the 15.81. So we can calculate the Cohen D as like 0.32. As you can see that the differences between Cohen D and mean differences is that Cohen D consider the standard deviation. So that's very straightforward. And in terms of the numbers of Cohen D, it can be like, for instance, 0.2 can be considered as small, 0.5 considered as medium, and 0.8 considered as large. So this is based on Jacob Cohen's book. I put a book name here. Look at these three numbers, you might get a conclusion that, okay, maybe all the Cohen D numbers are smaller than 1, but actually that's not the case. In some cases, actually Cohen D can be greater than 1. So this is another example. So the first group of number is 1 to 5, the second group of number is 6 to 10. Of course, there could be different number. Here I just made a very, keep the example very simple and straightforward. And here the mean differences is still 5. 8 minus 3 is 5. But then the standard deviation, as you can see, that is pretty small. It's 1.58. Since that the numerator is greater than the denominator, we can get the Cohen D, which is greater than 1. So now we get the basic idea about Cohen D. Let me just use some example in R to show you, to help you better understand the basic concept of Cohen D. I wrote this document in R Markdown. Let me just click here simple. I'm not going to go to R Studio. So here, just like the mean difference is 5, standard deviation is 1.58. Okay, just one side note is that when I calculate the standard deviation, I assume this is sample standard deviation rather than population. But regardless, when I simulate this, so this is theoretical value. Anyway, so the mean difference is here, the simulated data. For the first group is 100 number, another group is 100. Actually, so this is the total sample size 200, rather than the sample size here is 10. 5 is 10 total sample size. But here, that the total sample size 200. But we keep the effect size as the same, 3.16. So the mean difference is 5, standard deviation 1.58. And then since that these are two group of number, we can use t-test to test whether the mean differences reach the significant level. And we got a p-value is, this is 2.2, and this is exponential minus 16. So that means that the p-value is very small, definitely smaller than 0.05. And so that we conclude that, okay, these two mean, the mean differences 5 is significant. So we keep the mean in the next example. We keep the mean mean difference is 5 as the same, but we increase the standard deviation. So here, basically, I try to illustrate that the differences between mean differences and the Cohen D. So we keep the mean differences 5 the same, but we increase standard deviation. Then the effect size decreased from 3.16 to 0.5. And we keep the sample size the same, 200. And here we get the p-value 0.02, which is greater than the p-value earlier, yes. But still is significant, smaller than 0.05. So that we can still conclude that the mean differences of 5 is significant. And if we do it further, we increase the standard deviation into 20. And in this case, we got a p-value 0.69. That means that it's not significant. The difference is not significant. The mean difference is of 5 it's not significant because effect size now become like much smaller. So we can, all these examples, we can basically observe that the mean differences is kept the same 5 here in these examples, and the different standard deviation lead to different effect size, which lead to different p-values. For the same sample size here in these 3 examples, we kept all the sample size to be 200. Large effect size will lead to smaller p-value. So earlier the effect size large, yes, p-value is smallest. As the effect size become smaller, the p-value become larger. So that's the basic idea about Cohen D. And so I explain what a Cohen D is, and also I use some examples to explain further. And if you have any questions, feel free to comment down below, and I'll do my best to answer the questions you might have. Okay, thank you for watching.